Okay, today's lesson is about acid and base equilibrium. It's a continuation from equilibrium, but we're looking on just acids and bases. So here are some pictures just showing you regular acids and bases that you are using every day. And some are acidic and some are basic. So we're going to be seeing how this ties in nicely with equilibrium. From grade 11, you recall we looked at properties of acids, and we're not going to be asking you those questions specifically. But these are just something that you should know. Very good multiple choice type questions. So an acid produces H3O plus ions in solution. And by H3O plus ions, we mean hydronium ion. And the hydronium ion, so as for grade 12, we're not going to talk about H plus, we're going to talk about hydronium ion, so that's H3 plus ions. So it's just a hydrogen ion attached to a water molecule. So you know you have a water molecule here that had two lone pairs from your grade 11, and then you have a H plus. Because the H plus is empty, this can donate its electron to that, and we end up with an OH3, and you have your brackets here, and then you have a plus sign, and that's our hydronium ion. Okay? So an acid tastes sour, corrode metals, are electrolytes, react with bases to form salt and water. That's not really a definition. We know that from grade 11, a salt is just an ionic compound. So please remember that. pH is less than 7. We will be doing pH calculations. And it turned blue litmus paper to red. We have also universal indicators that we use. Bases. Bases, on the other hand, we have a dishwashing liquid here that is a base. Bases produces OH minus ions in solution. If you recall from grade 12 organic, it's called the hydroxide. So I call this OH minus ions. Base tastes bitter. I say B for base and B for bitter. So that's one way of remembering. They are also electrolytes, just like our acids. They feel soapy or slippery. So remember, we can use dishwashing liquid as a good reminder. They also react with acids to form salt and water. So acid and bases basically have the same. The pH is greater than 7. So remember, the pH scale goes up to 14, and it turns red litmus paper to blue. Okay? Basic blue is what we use to remember it. So those are just basic definitions. Characteristics. So we're going to be looking at definitions for acids. Definition for acids, we have 3 basic definitions. You looked at definitions in grade 11. We're going to go through them in more depth, and we're going to review conjugate acids and bases as well before we actually get into the equilibrium. So the first one, Arrhenius definition. Arrhenius states that an acid is a substance that produces H3O plus in water. So therefore you have this hydrochloric acid reacts in water and it produces our H3O plus. Okay? And then our Cl minus. So Arrhenius is somewhat limited because it only looks on when we have our acid in water. So limited because it only deals with aqueous solutions. Okay, and now our acid here, H2O, move from H2O to form OH minus ions. So it's from H2O to OH minus ions. Therefore, it lost a proton. So therefore, it's a proton donor. So it's a proton donor. So an acid donates a proton and it forms OH minus ions, and this is called our conjugate base. So every base has a conjugate acid and every acid has a conjugate base. Okay, so another example of a conjugate base pair, this HCO3 minus plus H2O to give you H3O plus CO3 2 minus. So if these two are connected, and then these two are connected here. So you look, HCO3, so we had HCO3 minus going to CO3 2 minus. So this one lost a proton. So it donated a proton. So proton donor. Oh, actually it should go on the other side. So let me erase this. So it's for the HCO3 minus. That's actually a proton donor. So a proton donor. So this is an acid. It donates a proton, and this becomes our conjugate base. And our conjugate base, I'm just going to start calling it CB for conjugate base. Okay, and I want to look at the relationship so we can come up with a relationship between conjugate base pairs. And this is our base, H2O, then it went to H3O plus, so it gained a proton. So this is our base, and this is our conjugate acid. Okay, let's look at the relationship between an acid and a conjugate base. So HCl is an acid, it donated a proton, and it became Cl minus as our conjugate base. So our conjugate base is negatively charged. These are some of the things I want to study when you review. It is negatively charged. It has one proton less. Than where it came from. And the next one, what about the charge? This was 0, so the charge went down by 1. Okay, so make sure when you're studying, you study this. A conjugate base is negatively charged. It has one proton less than the acid where it's coming from. So we could put this than acid. Sorry for that mess. And the charge went down by 1. So a conjugate acid, on the other hand, it is positively charged. As compared to the other one, that one has one proton. So look at this, it has one proton more. One more proton than the base. And what about the charge? Look at the charge. The charge went up by 1. These are two good examples to use all the time. So these are things that you'd study. But if you use HCl to Cl minus and NH3 to NH4 plus, those are two very good examples that you should use. So those are definitions for Bronsted-Lowry. Remember, an acid is a proton donor, a base is a proton acceptor. They form acid-base conjugate pairs. And then for questions, you're normally asked to identify the acid-base pairs. Very useful when we come on to doing equilibrium calculations for titrations later on. Okay, so learning check, let us do this quickly, although the answers are already there. HCl to this, so the first thing I would do, always trying to make the connection to see which two are connected. Look at the relationship, so therefore this becomes the acid because that last one, that's a conjugate base. That's the base, and then that's the conjugate acid. The connection here as well, these two are connected, and those two are connected here. So we have H2O is acting as a base, that's its conjugate acid, and sulfuric acid here is acting as an acid, and this is our conjugate base. Sometimes you're given just the reactants and asked to write equations representing the conjugate acid and the conjugate base pairs. Okay, so the examples in your workbook, you could probably stop now and do examples in your workbook. The third definition is Lewis definition. And Lewis definition is called the universal definition. And universal definition because simply this deals with electrons. Every atom has electrons. Atoms come together to form compounds, and the compounds have electrons. So all compounds have electrons, so that's why that is universal. A Lewis acid, a substance that accepts an electron pair, and a Lewis base is one that donates an electron pair. We're not going to be doing calculations based in equilibrium based on Lewis definitions anyway, so you just need this not mostly for multiple choice or for true and false. Okay? So the definitions that we'll be using for calculations are Bronsted-Lowry for conjugate acid-base pair and Arrhenius actually for our equilibrium calculation. Now I want to ask a question. If we have H2O, I hope you realize our next topic is going to be H2O. H2O can act as an acid or as a base. So if it acts as an acid and if it acts as a base, what will we end up with? So as an acid, H2, an acid is a proton donor. So if it donates a proton, it's supposed to form a conjugate base. And we know that conjugate base have a negative charge, 1 proton less. So that's an H and an O, so we end up with OH minus. Whereas if it acts as a base and forms a conjugate acid, a base is a proton acceptor, so it's positive charge. It accepts 1 more, and that's what we're going to end up. So H2O is known as amphoteric. Means it can act as a base and as a acid. As an acid. Okay, so please remember that, especially when you're writing equations later on for equilibrium, water is going to be commonly used. We're going to look at the equilibrium constant for H2O. It can act as an acid and it can act as a base to form conjugate base and conjugate acid. Okay, we'll do one question from your workbook page 19. Page 19. So once you're finished this video, you can work with questions from page 19. But I'll do one question from question 15. And I'll just do the first one. It says HI plus H2O. And then you're to write the reactions. So here you have to write the reactions before you're given. So write one as acting as a conjugate acid or conjugate base. So for this, because H2O can act as an acid or base, we have to look at the other one. Is HI, and please don't go about making up compounds, can HI accept a proton or can it donate a proton? The only thing it is able to do is donate a proton. So right away it would form H minus. So if this is donating a proton, it is acting as an acid. That means that's a conjugate base. That means this has to act as a base. And if it is acting as a base is a proton acceptor, it has to accept a proton. So that is what you will get as your answer. So that is that's part 5B in your workbooks. So take some time now to finish the questions on page 19 from 1 to 5.